Hi everybody, this is going to be section 4.4 from our Hawks College Algebra textbook on the transformation of functions. So today what we're going to look at is we're going to look at the shifting, stretching, and reflecting of graphs. So we're going to take the parent functions or the original functions we looked at in the last section 4.3 and now change them a little bit, stretch them, reflect them, stretch them. So the first thing we're going to look at is horizontal shifting. So remember, horizontal shifting means that it is going to move to the left or to the right on the graph, so along that x-axis. And if you have horizontal shifting, what you would do is in your function, instead of having just f of x, you would replace it by x minus h. So really, what you're doing is to that original parent function, within those parentheses, you are either adding or subtracting a number. Now, when you add or subtract that number, it's going to make the graph move left or right. But the important thing to remember here is we have x minus h. So whatever you put in for h, it's going to be the opposite the way you think it should move. If we do x minus 5, I would think, oh, it's going to go to the left, or we're going to subtract it like it does on the number line. But because it is minus that h, or the opposite of h, if you subtract 5, it's going to shift your graph 5 units to the right. So a negative number, so minus a number, is going to move it to the right. So it's going to move to the right. And if you add a number like x plus 5, it is actually going to move it to the left. So just think opposite of what kind of like the number line is, or what you would think when you do a horizontal shift. Okay, so here we're going to look at our first of two horizontal shifts. We're going to look at first f of x equals x plus 2 cubed. And one of the things that they're always going to ask you, or they're going to ask you in future questions, is what was the parent function? What was the original just plain Jane function before any shifts or stretches or compressions were made? And in this case, remember, a horizontal shift, you're adding something to that x value. They added the 2. If we took that 2 away, our parent function would have been f of x equals x cubed. And as you can see right here, I'll trace it in red, this is our parent function that they graphed. Now they added 2. Remember, it's different than what you think. If you add 2 to the x value within those parentheses like that, you're actually shifting the graph 2 places to the left. So if I trace it in blue, here is the shift. It went over 2 places. So each point you can see, not because I've drawn on it, it's a little harder, but it shifts it over 2 places. So here it is at the origin, right here, and then 1, 2, there it is at the origin. And again, if I count other points, like right here, it goes over, excuse me, 1, 2, again, my drawing's not that fabulous, but it shifted the whole graph, each x value, 2 places to the left. All right, and so here, the original, or the graph that they gave us and they asked us to describe the shift, was g of x equals the absolute value of x minus 4. So remember, absolute value is that V-shaped graph. Again, if they were to ask you what the parent function is, I want you to think about it like before they did anything to the equation, what was the original graph? Okay, what we're looking at is a horizontal shift. We have that x minus 4 in there. But the parent function, or the one they started with, would have been g of x equals the absolute value of x. Or we have this graph right here. Okay, now they subtracted 4. So remember, it's the opposite of what you think. It is going to move to the right 4 places. So if you look, here's the vertex at the origin, and we count over 1, 2, 3, 4. There's the new point. And again, if you pick any point on this graph and move over 4 places, you'll have the new point on the new graph. So like here, if I look right here, I go 1, 2, 3, 4. All right, it's moved over 4 places. So the shift, because it was minus 4 within the parentheses or within the x value there, is a horizontal shift to 4 places to the right. So now we looked at horizontal shifting, but you can shift the graph vertically as well, or along that y-axis, so up or down. And then that vertical shifting is going to be your k value that you're going to add to your graph. Here, you're going to take the original function, and you're going to add or subtract a number, depending on the sign of the number. If you add a number, and this is just like it looks, if you add a number, it will be shifted upward, so it will go up. If you subtract a number, it will go down. It'll shift down on the graph. There's no tricks to the k value. Also, it's added outside of the original x value. You'll see in the next slide how it's different. All right, so what we're going to do is we're going to look at and sketch, which I'm going to show you printed out ones because it's easier, but sketch the graphs of the following functions. So our first function is f of x equals 1 over x plus 3. Now again, for this one, you want a parent function, and then you want to know like what's the change to it. In our case, our parent function is, you got to look for that, what's with the x. So our parent function here, or the original function they started with, was f of x equals 1 over x. And then they added 3 to that. Notice the 3 is outside of this x value. Because it's outside of it, it's going to be a vertical shift, which means it's going to shift up 3. So this one's going to go up 3. If it was a horizontal shift, and it's not, but if it was, it would look like this. It would be 1 over x plus 3, and that would mean a horizontal shift. And again, because it's plus 3, it would go to the left 3. So now for b, we're going to look at the graph in a second, but we have the cubed root of x minus 2, and that minus 2 is not underneath that radical. So this means it's a k value shift, and it is going to shift it because it's minus 2. It's going to go down 2. So it'll be down 2 spaces, or vertically down 2. If it was a horizontal shift, and it's not, but if it was, it would have been the cubed root of x minus 2 underneath the radical. But ours, it's not, it's outside the radical, so it is a vertical shift down. And here you can see, here's our first one. It was the f of x equals 1 over x plus 3. The dotted lines represent the original function, so right here. And then because it was plus 3, it moved it up 3. So you can see on both sides, the points have moved up 3 spaces each. And then one thing to note, they will ask you like domain and range. The domain isn't going to change because it didn't move left or right. It moved up or down. So the domain did not change. It's the same, but the range is affected because now instead of having 0 as your asymptote, or your the point where there are no parts of the graph, it is 3 because it was moved up 3 units. So your range did change a little bit. So that's something to note. All right, and here we go. We have the cubed root of x minus 2. And again, I don't know if we talked about it earlier, but the parent function would be just the cubed root of x. So here is our parent function. And because it's minus 2, it shifted everything down 2 places. So you can kind of see, like right here is kind of a good place to look. It goes down 1, 2, and it starts here, down 1, 2. So it shifts 2 down for each. For this one, your domain and your range, your domain is still going to be all real numbers, and so will your range. It will be all real numbers, or negative infinity to positive infinity. There's really no, because there's no asymptotes here, there's no change to that. Okay, so we've done our shifting, and now we're going to look at reflecting. Reflecting, it takes a little bit of getting used to figure out if it's reflecting. We're going to talk about if it reflects over the x-axis or the y-axis. If you have a function that is reflected over the x-axis, then what they're going to do is the whole function will be negative. So they would have that whole function, the negative sign would be outside the, think of it like the parent function. But If it's reflected over the y-axis, then just that x value is going to be negative. And again, we'll look at some copies of the graphs to kind of show you what I mean. It's a little hard when you hear it the first time, but I promise we'll make it easier. Okay, so here is our two examples. They want us to show how they were reflected. Our first one is f of x equals negative x squared. And for this one, the negative is outside the x value, or it's x squared, and then there's a negative on the outside. Because it's out there, we are reflecting the graph over the x-axis. Here was our original graph, and here is the reflection. So notice it was reflected over that x-axis. That's our reflecting line. So that equation was reflected over the x-axis. And then if you take a look for g of x here, the negative sign, if it was reflected over the x-axis, it would be negative square root x. But because it's on the inside, this means that it's going to be reflected over. And here is a picture of the equation reflected over the y-axis. The original graph, again, was y equals the square root of x, which is right here. And the reflection is over, again, that y-axis. Here's your line of reflection. If I were to fold it on the y-axis, the two sides will be mirror images of each other. And again, we'll look at more examples that kind of help you with this. It's a little hard in the beginning, but you'll get used to it, I promise. All right, and the last part of our shifting, stretching, and reflecting of graphs will be the stretching and the compressing of a graph. Just like when we have a parabola, that a value, we talked about it, how it can make it either a wider parabola or a narrower parabola. That is for any function, that a value. So a number times, the x squared, the radical, whatever, this will give you, if your function is going to be stretched or compressed, it will be stretched if a is greater than 1. So if you have like 2 or 3 or 4, it's going to be stretched. Which actually means when it's stretched, if you think like if you have a ball and you stretch it, or a ball of dough and you stretch it, it gets narrower as you stretch it. So if I take it and I pull it up, it's going to be stretched, it's going to get narrower. If you have a number that is a fraction, so a number between 0 and 1, like 1/2, 1/3, 1/4, then your graph is compressed vertically. So that means that if I were to take a ball and I were to push down on it, the ball would actually get, like a ball of dough, would get wider. So it would be compressed. So it's going to make it a wider graph. All right, so we're going to look at how these graphs have changed. The first one we have is f of x equals the square root of x divided by 10. Now, you're probably like, well, that's kind of crazy. And you're right, it is. But I want you to think more like, remember there's that 1 in front of the square root of x? So really, what we're doing is our parent function is the square root of x. It's really written like this. It's 1/10 square root x. So think of this 1/10 as your a value. Because it is a fraction, is it going to stretch or compress our graph? Make it narrower or wider? Hopefully you said wider, because we do have that fraction there of 1/10, so it's going to make the graph wider. And we're going to take a look at that in a second. Our second graph we have is g of x equals 5 times the absolute value of x. Now, this a value is a 5. It's greater than 1. So that means it's going to stretch our graph or make it narrower. And we're going to take a look at both of these in just a minute. All right, so here is our first one. We had our compressed graph because it was compressed to a function by 1/10. So the original function is the one in the teal. Our compressed one is the one in the blue right here. So it is, because all the coordinates have been multiplied by a factor of 1/10, they are smaller. It's compressed. And so for the next one was our absolute value equation. Here is the original function right here. And then it was multiplied by a 5, so it stretches it vertically, which means it gets narrower. So you notice this equation in the blue is a lot narrower than the original parent function. Okay, so when you do transformations and you look at shifting, stretching, and reflecting, you want to follow this order every time. You want to first look, are there any horizontal shifts? Is there any stretching or compressing? So think of your A value. Any reflections, so that negative sign is really what you're looking for in the function. And then any vertical shifts, so any shifts up or down. So it's not quite exactly the order that we taught it in, but that's what we're looking for. So let's take a look at just one to kind of help you guys. So if I give you g of x equals -2 times the square root of x plus 1 plus 3. All right, so we are going to look for first any horizontal shifts. Remember, horizontal shifts would be with the x, either under the radical, with the exponent, whatever it is. So I have the square root of x, which, if I asked you for the parent function here, if you take away all the other numbers, your parent function for this would be, oops, sorry, it's a little low, g of x equals the square root of x. So they added 1. Because they added 1, that's going to be a horizontal shift. And we're going to shift it left 1 unit. So I'm going to write on here, left 1 unit. All right, stretching and compressing. When we're looking for that, we're looking for an A value. So you're looking for a number that's multiplied times that function. We have here a 2. The sign of the number doesn't matter. Only that 2 matters. Because it is greater than 1, that means that we are stretching the graph vertically. So we are not compressing, but we are stretching our graph. So it's going to get narrower. All right, now the reflections, and this is where it gets a little hard. You have to look for that negative here. Because the negative is outside of the parent function, so it's outside of the g of x, that means that we are going to reflect it over the x-axis because you have that negative outside. If it was on the inside, so if I put it in here, then we will reflect it over the y-axis. But because it's on the outside with that A, we are reflecting over the x-axis. All right, and vertical shifts, remember that is going to be like this number hanging out right here. Because it says plus 3, that means that we are moving this equation up 3. So we are moving it up the y-axis 3. We are vertically shifting it up 3. Hopefully that helps. You guys will be looking at a lot of these on your homework and in some classwork. Okay, now they want us to sketch this graph. Really, what I want you to be able to do is describe the change in the graph. So this one, it's kind of written a wonky way. It's not written in the best way because it's 2 minus x there, which I think makes it a little hard sometimes to read. What I would do with this is, 1, could you figure out the parent function? For this one, because you have the 1 and then you have the x on the bottom, your parent function would be f of x equals 1 over x. So that's the function they changed. And then we're used to seeing like the x value first. So I'm going to help us out here. I'm going to rewrite it and make it 1 over. And I can rewrite it as negative x plus 2 because I think that really kind of helps you see the equation a little bit better. Now, if they want us to describe a transformation, okay, horizontal shifts, what you look for first. Notice they've added 2 down here to the x. So that means because it's down here with the x and they've added 2, we are going to shift this graph 2 units to the left. So it will shift 2 units to the left. Okay, now what we need to do next is any stretching or compressing. Because I don't see here any a values, numbers other than 1 with the x, or -1, doesn't really matter, but there's no stretching or compression. Reflections. Now, there is a reflection. There's a negative. Whenever you have a negative with the x, you got to look for a reflection. Because the negative is here with the actual x and not outside the whole function, so it's not here, not outside the whole function, because it's here, you are going to reflect this graph, and it is going to reflect I didn't spell reflect right. Oh my goodness gracious, people. I'm sorry. You get the gist of it. But let's see here. It is going to reflect. Let me put the L in there. I can't even write. Over the y-axis. Because it's down here with the equation. If it was outside, it would be over the x-axis, but it's down here with the x, so it reflects it over the y-axis. And then there's really no vertical shifts because there's no plus or minus a number right here, which is where the vertical shifts would be. If it was plus or minus a number here, it would be a vertical shift, but there isn't any. So that would be our graph. Okay, and here is our reflection, our transformation of our graph. Again, they did it 1, it should be -1 over -x plus 2. Here was the original function for the first graph. Then they shifted it to the left 2, and then they reflected it over the y-axis for the last one. All right, so the next thing we're going to talk about is symmetry of functions and equations. This is something that we're going to mention briefly here. You're not going to do a lot with it on the homework. This is something you'll look at in other courses more in detail. But your equation, remember symmetry is like if I fold this on, if it has y-axis symmetry, if I fold it on the y-axis, my graph would be exactly the same on both the left and the right sides. It would be the same if I folded it vertically. All of your even functions have symmetry about the y-axis. And what they're saying here is if I replaced, if f of -x, or the opposite of x, is equal to f of x, for x in all the domain, then it's an even function. Origin symmetry. If they are symmetric about the origin, that's going to be your odd functions, which we've looked at before. And that means if f of -x is equal to the opposite of f of x, then it has an odd function. And again, we're going to look at the graphs in a second to see these. And I know kind of what I told you earlier was a little confusing with the symmetry, but here is kind of something to break it down a little bit. If you have y-axis symmetry, think your even functions. If you replace x with the opposite of x, so if x was 3 and I replaced it with -3, I would get the exact same y value. That's your even equations. Your x-axis, if I replace y with the opposite of y, and I get the same equation. So again, if my equation equaled 5, and then I did the same thing again and I got -5, or I used -5 as my answer to my y, and I solved it, I would get the same thing I would get if y equaled 5. Your origin, again, is your odd equations. And that is if I replace x with the opposite of x, I get the same equation, but I also have to replace y with the opposite of y to get the equivalent equation. Again, something I just want you to kind of be aware of, but it's not something we're going to delve too deep into in this course. You'll look at it in other courses. All right, and here we have 3 graphs, which we're going to look at in the next coming slides, which really just kind of show you the symmetric about the y-axis, the origin, and the x-axis. So let's take a look at those, and we'll talk about them as we go through it. Okay, so here, we have an even function. We got that x squared there. And this graph, if you look at it, if I were to fold it on the y-axis, it is symmetric about the y-axis. So this is what they're talking about, symmetry. If I fold it on the y-axis, it is symmetric there. All right, and here's an equation that is reflective about the x-axis. It is not a function, as you can see, like it would not pass the vertical line test, but it is reflective about the x-axis because if I were to fold it on the x-axis here, the same graph would be above and below that line. But again, it's not a function, but it is a relation, and we do have things we look at that are reflective on the x-axis. Okay, the last thing we're going to look at in this section is when is a graph, or like when we look at a function, when is it increasing, decreasing, and constant? And basically, if it's increasing, again, you read a graph from left to right, like you read a book or a page in a book. If it's increasing, I always think it's going uphill. If it's decreasing, it's going downhill. And then if it's constant, it should be like a straight line, or in some cases like a point that's there. It's not going to change. So we're going to take a look at a graph in the next slide. We'll talk about when it's increasing, decreasing, and if there's any constants in there. Okay, so we have a parabola here. It's x minus 2 squared. So again, they shifted it to the right 2 places. Minus 1, and they moved it down 1, so that had a horizontal and a vertical shift. When we look at this, again, you read a graph from left to right. So when I look at this first part of the graph, and really, like your vertex is kind of going to be your midpoint there, or where it's going to shift. So from the first part, from left to right, even though it has this arrow here, it is going downhill. So my graph, because it has that arrow there, it is decreasing from negative infinity until we get to, and you always look at the x value here, so a 2. So it is decreasing from negative infinity to 2. Then from here, we look, and that from that point on, from 2 up, and we're looking on our y-axis, it is not a very good line, but it is increasing. So it's going uphill from there. So our parabola is increasing from 2 to positive infinity. And around the 2, because it's not decreasing at 2, it's not increasing at 2, it's kind of stopped there, we put parentheses. So this one is where it is decreasing, and here it is increasing. And really your vertex, and I misspoke in the other slide, but the vertex here, it's not a constant point, it's just kind of where the graph shifts. So this one, unless you have like a straight line, there's no constant part to it.